All right, so welcome to the third lecture. So in the previous two lectures, what we did is, so for the first one, we studied some distributions, which were not, which are a little bit more advanced than what we learned before, including we studied a little bit of gamma distribution, chi-square distribution, and students T distribution. After that, in the last class, so we have seen how the sample mean and sample variances are used for various computations. For instance, we have seen how we can use the maximum likelihood function for estimating the value of theta from the parameter values. And today, what we'll be doing is we'll be studying the confidence interval. So let me just switch my camera. Okay, so today we'll be studying the confidence intervals of the parameter estimation. Okay, so this is the Stat 313 lecture 3. So we how to find the confidence intervals. And what does it even mean? Okay. Now, if you recall, when we considered or when we found the value of when we studied this f of x theta, where theta was in some set omega, and theta is unknown. In the last lecture, we have seen how to find theta. So to find theta, we use the, remember those step 3, like 3-step procedure. So we use the maximum likelihood estimator. Okay. What we eventually found, is theta hat. It's an estimator. So it's a function of all those sample variables, x1, x2, xn, where this x1, x2, xn is a sample from distribution x. Distribution x. Remember, this x1, x2's xn is a sample from distribution x. Also, so this really means that this is IID. So they are independent and identical distributed, and the distribution is x. Right? So now the question is, suppose you find this theta hat. Okay. Now there is an ideal theta, right? Like, so we don't know theta, so that is why it's unknown. What we did is, based on a sample, we computed this theta hat. It's unlikely this theta hat will match with the true value, because this is something based on the sample. So suppose we are trying to estimate the say the average height of a country. Okay, and suppose we just compute the average height of students in a classroom. It is no way a proper representation of a country, and also it will not really give you the correct theta in that case. But what you're getting is theta hat. So it's an estimation. It's the best you can do, but it's not really the exact value of theta, right? So the question is, um, uh, how much error are we making by estimating theta with theta hat? So in the last class, whatever we have done, so we tried to make an estimate of theta hat based on sample. The question is how much error we are making. So we'll be discussing this. So, or another way to put it is, this is a nicer way. By how much, or by how much did theta has miss theta? Okay. Now this is, we'll be trying to explain this thing in this section, and this error is estimated in terms of the confidence intervals. Okay, so it's so answer is in the confidence interval. We'll see what it means. Okay, so here's the formal definition of the confidence interval. There's a mathematical definition. So let x1, x2, xn be a sample on a random variable x. What does it mean? So these are IIDs, and the distribution is the same as the distribution of x, where x has PDF f of x comma theta. I'm assuming that this x is continuous and it has the PDF of x theta, where theta is in omega, and of course this theta is unknown. Let 0 less than alpha less than 1 be specified. Okay, the first assumption is that we have an IID, we have a sample, and suppose somebody gave you a number between 0 and 1. Okay. Let us consider two statistics. So let L be equal to L of x1, x2, xn, and U be x1, x2. It's a function of x1, x2, xn. Be two statistics. Again, what does it mean? The word statistic means a function of the samples. So here we have x1, x2, xn is a sample. So any function on that, it's called a statistic. There are two statistics. Well, there are two of those statistics. So we call it statistics. Okay, this is not really the statistics that you're talking about. It's a plural of statistic. Okay, so we have two statistics. Now we say, here is the confidence interval definition. We say that the interval L to U is 1 minus alpha 100%. So it's basically we're multiplying this 1 minus alpha to 100, and then we convert this to a percentage confidence interval for theta if 1 minus alpha is probability theta is in this interval. We'll see how it goes, but this is the definition. Okay. So what it means is that the probability that the value of theta is lying between L and U is 1 minus alpha. An example would be, suppose you found a statistic L based on some sample. So maybe you're trying to estimate the value, estimate the theta, right? So now suppose you found a statistic L which is having the value of 100, and you found the value of U to be, say, 102. No? Now, probability that theta is in the interval of 100 to 102. Another way of writing this is probability of 100 less than theta less than 102. That is something, whatever that probability is, we'll call this equal to 1 minus alpha. Okay. And this is called the 1 minus alpha confidence interval. That means with probability 1 minus alpha, forget about this 100%. So it's just converting the probability into percentage. It says that with probability 1 minus alpha, the value of theta is lying between L and U. So you see what we are trying to do. So we would like to make this probability high. So higher this probability, it's better for you, for us, right? So because if we know that with maybe say 99% probability, say 99% chance is there that a parameter theta, suppose this is between 100 and 102, so that's a fairly good chance that the actual theta is between that, right? So once again, so what we are doing here is this is the actual value of theta. Okay, so it's computed based on two statistics. Okay, we'll see some examples, so it'll be more clear. So what we are doing here is based on, remember, so based on, so we have some we computed some theta hat, so based on the sample, so that is sort of encoded in L and U. Okay, and now the question is, what is that real theta that we don't know, that's unseen? What's the probability that is between that two values? And that is the answer. Okay, so we are trying to estimate how much or where the real probability or where the real theta is. Okay, because whatever we can observe or whatever we can compute is this theta hat, right? We cannot see the real, it's unknown, so there is a difference. Now the question is, I mean, how can you, what is the difference? So that is that is encoded in this confidence interval. So we'll see this a little better when we do some example. Okay. So just in words, the probability, so the probability that the interval includes theta is 1 minus alpha. Okay. Okay, and this 1 minus alpha is called the confidence level of the interval. So it's called the confidence level of the interval. That means how confident are you that your actual theta is between that interval. And by interval, I mean LU. Okay, that particular interval. It'll be much more clear when we do some real examples, but we'll see. Okay. Let's see. Let's do an example. Okay. This is called the confidence interval of mu. Say confidence interval for mu under normality. I'll explain what it means. But this is a good example which shows how to compute the confidence interval. Okay. So let's start by saying that our traditional assumptions. So let's start by saying that suppose the random variables x1, x2, xn are random sample from a normal distribution with mean mu, variance sigma squared. Once again, what does it mean? It means that this x1, x2 up all the way up to xn, they are independent and identically distributed. And what is the distribution? So the distribution is normal mu sigma squared for the population. Okay. Now let us define, as we have done in the last class, let's x bar be the sample mean. What is that? So that means this is 1 over n, summation I from 1 to n, xi. Whatever we are observing in the sample, we take the average. And that is what we call the sample mean. and S squared is the sample variance. Please note that this S squared is given by 1 minus, we're dividing by n minus 1. So it's I from 1 to n, xi minus x bar squared. That's the definition of S squared. So that we have been discussing for the last two classes. Also recall that actually when we try to have a maximum likelihood estimator for mu, so the maximum likelihood estimator of mu is x bar. So the maximum likelihood estimator for mu is this quantity x bar, but the maximum likelihood estimator of sigma squared is not a squared. Okay, so it is reimbursed. It's basically 1 over n thing. So it's given by n minus 1 over n s squared. So we have done this last class. This is unbiased. Sorry. This is the first one is unbiased estimator. This is a biased one. So this is the unbiased, and this is the biased. Okay. Okay. Now let's see. So let's now consider a distribution. So with this setup, then consider x bar minus mu over s over square root of n. Okay, and at this point, I'll show you something from the first class. I don't want to rewrite it. So let me just show you. Okay, so we'll consider this and we'll call this one to be, say, T. Now observe at the first class, we wrote this theorem. It's called student's theorem. So this is from the first class. Okay. It says that if x1, x2, xn is ID, and it follows a normal distribution mu sigma squared, we define this x bar and s squared that we are doing. And then it has some properties. For example, so x bar follows a normal, x bar and s squared are independent. So that's fine, but we don't need it at this point. Third one is this follows chi-square, but fourth one, okay, so T is x bar minus mu over s over square root of n, and that is exactly what I wrote. Okay, this has a student T distribution with n minus 1 degrees of freedom. That's what the theorem says. Okay, so what we know is this quantity that I just wrote. So this follows a student T distribution. Okay, so it has a then consider this. It has by I think we call it student's theorem in the first class. By student's theorem, first class. So then this by student's theorem, it has T distribution with n minus 1 degrees of freedom. Okay. Good. Now, at this point, so what I want you to do is you have to will be using some notation, but then later on I'll show you a easier way, because nowadays you can I mean, when we learn statistics, we had to use a table, but now you can find a lot of tools online which you are welcome to use. I'll show you some, but let me just first finish this and then I'll show you what to do. Okay. All right. So we have this one. So this is the setup. The setup is that we have a sample, and we are constructing random variable t. So that this random variable t we'll be playing with this. Okay? So for suppose now we fix an alpha, which is between 0 and 1. define the value t of alpha over 2 comma n minus 1 to be the upper alpha over 2 critical point of a t distribution. T distribution with n minus 1 degrees of freedom. What does it mean? It means if I have the t distribution, I'll show you a picture shortly. So suppose this is a t distribution. This area is alpha over 2. And this point is t of alpha over 2 n minus 1. So that's the meaning. Okay. So what it means is really alpha over 2 is probability that the random variable t is more than this one. So t of alpha over 2 n minus 1. That is. And it's clear from the picture. So what did you do it? So you give me an alpha between 0 and 1. I know what is alpha over 2, so that is this region. So I can always find, and you don't have to do anything. So I'll show you how to find it from online from online resources. Okay, so far so good. So therefore, we can do an actual calculation. So 1 minus alpha is equal to probability. Okay, so this is alpha over 2, and this is a symmetric distribution. So this will be also alpha over 2. This is 0, and this point is minus t alpha over 2 n minus 1, right? So that means if I want to compute this 1 minus alpha, so 1 minus alpha is what? So 1 minus alpha is really 1 minus alpha over 2 plus alpha over 2. So I'll subtract, this total area is 1. I'll subtract this area and this area. So I ended up with this area, right? So this is basically the value of the t is between this and this. T distribution is symmetric. We have discussed this in the first class. So this is going to be t of alpha over 2 n minus 1 less than t of alpha over 2 n minus 1. Do you agree? So 1 minus alpha, so that means I'm talking about the probability of this unshaded region. That is, so basically, this is the probability that the random variable t takes the value between these two, right? Which is same as probability of, now let's spell out this t. So it's t of alpha over 2 n minus 1 less than x bar minus mu over s over square root of n. That's the value of t, right? So we just wrote t less than t of alpha over 2 n minus 1. Okay. If I simplify this, it becomes minus, so let's multiply with this quantity s over square root of n, s over square root of n less than x bar minus mu less than t of alpha over 2 n minus 1 s over square root of n, right? In terms of mu, this is therefore, it's x bar minus t of alpha over 2 n minus 1 s over square root of n less than mu less than, I skipped a step here. So basically first you subtract minus x and then you flip the sign. You'll have a negative mu bound. And then when you have the positive mu bound, you flip the sign of the inequality. So it's x bar plus alpha over 2 n minus 1 s over square root of n. Then that's it. Okay. This is the result we found. So 1 minus alpha is this one. Let me box it. Okay. Now let's compare that. So this is this seems to be pretty abstract, but let's compare that with what we had before, the definition of the confidence interval. What is a confidence interval? So here's the definition. So you have to find two statistic two statistics. One is L and other one is U. So suppose this is my L and this is my U. Why are they statistic? Because they are computed based on the sample. Okay, if you give me a sample x1 through xn, I can always compute all these numbers. Okay, so you see that the probability that the value of mu is in between L and U is given by, and mu is an unknown here. So so we are trying to estimate what is the exact mean of the distribution. So mu between these two is the with probability 1 minus alpha, right? And now look at this one. So this is basically theta, which is in our case mu, is between two numbers. I wrote it this way. So see that this is really probability of L less than theta less than U. Okay. Between 1 minus, so theta is between L and U, the probability is 1 minus alpha. We have the same setup. So you see that how it works, right? Okay. So that means once we draw a sample, how does it work in practice? So suppose I'll do an example, but just very quickly. So if you draw a sample and if you compute a number, so suppose you compute the value of this x bar and you got some number and you'll compute this s and you get some number. So basically the probability of that mu is between that two is computed based on whatever fixed alpha is there. I know this number and I'm done. Okay, so let me just write one more step and then show you a concrete calculation based on this one. It's very important. So once a sample is drawn, that means you can see the numbers. Let little x bar is the realized value of x bar. What does it mean? It means that the value of x bar for a particular 10 numbers. Okay, so this little x bar, remember that this is always a random variable and this is a value of the random variable, right? And suppose that we have s squared is the realized value of s squared. Once again, s squared is a random variable. That's the sample variance. And suppose for a particular sample, we see we compute this and we got little s squared. Okay. Then 1 minus alpha 100% confidence interval for mu is given by x bar minus alpha over 2. So I'm basically writing the previous expression with I'm just replacing that big x bar with little x bar. N minus 1 and then s over little s over n 2 x bar plus t of alpha over 2 n minus 1 s over square root of n. So this is a minus sign and this is a plus sign. That's the only difference. Okay. Okay. So this is the confidence interval for based on a particular. So this is a confidence interval because if you are having different realizations, these numbers will be different. So that is the confidence interval. So this is the interval is referred to as the, as I mentioned, 1 minus. So this is 1 minus alpha 100% t interval for mu. Okay. T interval because later on we'll do some other intervals too. So why it's t interval? It's based on the t statistic. Okay. All right. So that is the quantity. Once again, just to briefly recap. So we have this expression 1 minus alpha equals to this one. So what I did is for a particular realization, we have x bar equals to little x bar and big S is little x. So this quantity, I just replace this by little numbers like x bar is little x and big S is little s. And then we created this interval and we said that mu is in between that two is having a probability 1 minus alpha based on that sample, based on that particular sample. So that is a confidence interval. Okay. So now let's see. Let's consider an example at this point. And here is my example. Let's see. Um, I'm talking about problem number 4 points. So here is an example problem. So exercise 4.2.7. Okay. And this, I'll show you something else along with this problem. How to find that t value. And the problem goes like this. Let a random variable, sorry, let a random sample size of size 17 from the normal distribution n mu sigma squared yield little x bar equals to 4.7 and s squared equals to 5.76. The question is, determine a 90% confidence interval for mu. Okay. So then let's handle this problem, and I mean, this will give you a nice way of um, practicing some of the stuff. Okay. Solution. All right. So we are trying to estimate mu, 90% confidence interval. So 90% means it's 0.9, right? So if I look at the expression, let me just rewrite the last expression that I wrote so that you can see it better. So the last expression that I wrote was in a little different way. 1 minus alpha is probability based on the sample. Okay, so x bar minus t of alpha over 2 n minus 1 s over square root of n less than mu less than x bar. So I'm just basically writing this thing in terms of an interval, and that is equal to the probability of that is 1 minus alpha, right? So it's x bar plus t of alpha over 2 n minus 1 s over square root of n, right? For this particular problem, we are given with, we know the values of x bar and s. Okay, so what are the values of x bar and s? So this is, okay, so we want this to be 90%, right? So we want this to be 0.9. So what is alpha? So that means 1 minus alpha is 0.9. So alpha is 0.1, right? If 1 minus alpha got to be 0.9, alpha got to be 0.1. Okay. This is equal to probability of what is x bar? X bar is given to be 4.7. So it's 4.7 minus t of alpha over 2. Now, if alpha is 0.1, alpha over 2 is 0.05. N minus 1, what is the degrees of freedom? It has a size 17. So degrees, so n is 17. So n minus 1 is 16. S is what? S is, it's a square root of 5.76. So it's the square root of 5.76 over square root of 17. It's less than mu, less than, I'll write the same thing except with the plus sign here. So it's 4.7 plus t of 0.05 comma 16, 5.76 over 17. Okay, that's the expression. So you know that you almost know the answer now. So you computed this one as alpha over 2. So this one is alpha over 2. That's why from here to here, you find the alpha, and that is something is used here. Okay. All right, so you see that the confidence interval here is this and this. So I mean, how do you compute this number? So all I need to do, I have to compute the value of this one. So the only thing that is unknown here is this t of this one, right? And this t of this one. If I can find it, I'm done. Now at this point, let me pause and show you show you a way of computing the t distribution. So let me just share the screen. Stop sharing the screen. Okay, I hope you can see it. So what is going on here is, I'll send you this link to you. So this link is, let me just, I don't know how I can make it bigger. So this is, if you go to datatab.net/tutorial and then /t distribution. I'll send you this link. So this really gives you a way to compute the critical value. So without going into the table. So going to the table is fine, but since now we have a much better, I mean, a much quicker way of doing it. Now, when you go to this chart or website, you'll see the t distribution table. Now, please note that there will be two different kinds of tables. Okay, so one is one-tailed and the other one is two-tailed. Okay, you'll click on the one-tailed. It's not the two-tailed version. Okay, so one-tailed. There is a difference between these two. Okay, so what it does is now you'll not look for the first table. Go to the second table. Okay, now for the second table, you see the p-value. The p-value is the value of alpha that you're looking for in this case, and the value of alpha is the, I mean, or the whatever the well, so sorry, not the value of alpha, so the value of alpha over 2. So basically the p value is the area of this region, this brownish region. So that is the value of alpha over 2 in our case. So this is, in our case, it should 0.05. Okay. And what is this degrees of freedom? So degrees of freedom in this case is whatever you're trying to compute, because remember, so let me just go back here one more step. Let me stop the share. Um, okay, you see that we are trying to compute t of 0.0516, right? So that means in this case, this is my degrees of freedom. Okay, and this one is the p-value. Okay. Now, what is the value? So now let me share the screen again. So your p-value is 0.05, degrees of freedom is 16. So what is it getting? It gets me 1.7746, right? So now once you have this 1.746, so that is this number, and that is it. So you can use that here, 1.746, and that's the t value. So t of 0.05, 16. Okay, now you can simply use it in the previous expression. So we get 0.9, so is equal to p of 4.7 minus 1.746 times square root of 5.76 over square root of 17 less than mu less than 4.7 plus 1.746 square root of 5.76 over square root of 17. Okay, I have this calculation. So if you calculate this, so you get 0.9 is this one will give you 3.68 is less than mu less than 5.72. So what is the answer? So the question is asking for the confidence, 90% confidence interval. So 90% confidence interval for mu is this two numbers. So from this interval, right? So it's 3.68 through 5.72. Okay. So what we found is we remember, so that is the answer. Okay. So this, what we really did is based on this data set. So X bar is 4.7. So you may tempt to believe that this X bar is the representation of mu. Now you're asking the question, how much trust should I have in this decision that that mu, the actual mu is 4.7? The answer is well, we know that the value of mu between this interval 3.68 and 5.72, where incidentally 4.7 sits. So 4.7 sits in this interval. So we know that the value of mu between these two number is there's a high chance, 90%. Okay. So that is the um, estimate that you are making. Okay. And based on your sample mean. So the chance that you can trust this result is up to you. Well, I mean, the final decision is up to you, but the chance that the value of mu is between these two, based on the samples, based on those samples estimations, is this two. Okay. Question. If you have any question, please send me by email or send me the questions or ask me the questions during the office hours. Okay. Okay. All right. So this is something using t-value. So now there is another one. We know, I mean, this calculation is very nice, but it's sometimes it's a little tedious because well, we have this is an exact computation, but I mean, it involves some t distribution, and then we have to compute these numbers and we have to find it. There is another way of doing it. Okay. One drawback of this method is the x equals to x bar minus mu over um, s over square root of n. It depends on, so when we constructed this, if you assume, if you see what we did before, let's see if I can find it. That was the assumption for the building the confidence interval. There was an assumption which is written here. So confidence interval for mu under normality, meaning that we assume that the sample was taken from a normal distribution for sure. Okay. If that is not the case, then the entire derivation may not be valid because then, I mean, suppose it's drawn from some other distribution. So then the sample mean and sample variance are the same, but these two are not the same, right? So the maximum likelihood estimation, it may be different. We have done a lot of different maximum likelihood estimator. Here, everything is based on the fact that the original distribution is normal, but these things will change, and consequently, everything will change. So in other words, the drawback is this. It depends strongly on the normality of the sample items. Okay. So that is a drawback because the sample items can be may not be not normal. However, and we'll write the we'll study this in details in the next section. But however, this assumption is not really a bad assumption because we have a very powerful central limit theorem. I'll write the central limit theorem, CLT. Central limit theorem tells us that this is approximately true. Not really, but approximately. even if samples or sample items so this is approximately true even if sample items are not drawn from a normal distribution. Okay. We'll see what it means. I mean, but we'll not discuss it a lot. But what I'm trying to say here, this is a drawback, of course, that the samples may be drawn from some different distribution, and in this case, this T is not a. I mean, it will not be a T distribution. However, I mean, whatever we have done will not be accurate. But what is the central limit theorem that I'm going to write next is going to show is that even when this is this is not drawn from a sample or drawn from a population with normally distributed, this can still be thought of approximately normal. So let me just write this result. Okay, so this is like this. It's a theorem. It's a very famous theorem. So central limit theorem, or sometimes abbreviated as CLT. Okay. It goes like this. Let x1, let x1, x2, xn denote the observations of a random sample from a distribution that has mean, mu, and finite variance, sigma squared. Note that it's drawn from a distribution. We are not assuming that distribution is normal. But all we are assuming is that this notation may be confusing, but this mu is not the mean of a normal distribution. Okay, it's whatever it has, its expectation is, we call it mu. Whatever its variance is, and we are assuming that it's finite, we call it sigma squared. Okay, then the distribution function of the random variable w sub n, we are constructing new random variable, w sub n is equal to x bar. What is x bar? It's a sample mean minus mu. What is mu? This mu. Okay, over sigma over square root of n. What is sigma? That is the standard deviation of the original distribution from where the samples are drawn. And we divide by n, where n is a sample size. Converges to the distribution function of the standard normal distribution, n01. That's the standard normal distribution, as n goes to infinity. Okay, so please note what this result is saying. It's an amazingly powerful result. It says that even when the original distributions are not normal, all we know they have some expectation, and I mean the original distribution some expectation mu, and its variance is some sigma squared. Okay, now we construct a quantity from the sample. So x bar minus mu over sigma square root of n. This whatever, I mean, this is a distribution, and we are not claiming that this is normal. Or but what we are claiming is when n is sufficiently large, when n goes to infinity, this becomes a standard normal. Okay, this behaves as and there are many different kinds of convergence. We'll study it later. So I mean, it says that the distribution function. So the CDF of this distribution is going to the CDF of the normal distribution. So it's convergence in distribution. Okay, so now how can we implement this result? And this is a very nice result, and in the previous course you must have studied normal distribution in details. So we didn't study t like this t distribution in that details, but we studied normal distribution in details, so we should be able to implement it. Okay, so let's see one of the ways to implement it. Once again, goal is the same, the building the sample, building the confidence interval. So here is a example. Let's write this as example. Okay, so suppose that we have our n sample x1, x2, xn, our random sample on a random on a random variable x with e of x, the mean is mu, and variance of x equals to sigma square. What I cannot emphasize enough is this distribution is not necessarily random. The distribution of x is not necessarily normal. We are not assuming that x follows normal distribution. If x follows normal distribution, the calculation will be same as before. So we have studied this before. Okay? This is a new thing. So it's not necessarily a normal distribution. So, but it has expectation mu and variance sigma square for x. Okay. Now, in this case, we can construct, well, however, by the central limit theorem that I wrote. Okay, we can say that this x bar minus mu over s over square root of n. Okay, so this quantity, so if I define this as say z sub n by central limit theorem, this is approximately standard normal n01 for large n. We don't have to go to infinity, but for sufficient large n, this is the thing, right? Do you agree? Well, we should, because see what is going on is so here what we're estimating is we have some sigma squared as the sigma square as a variance and mu as the expected value. Now, an estimator for mu is x bar, and an estimator for sigma squared is s squared, right? So that is something we have seen before. So what we are doing here is the following. So we write instead of, so first of all, we started with x bar, and we subtracted this mu. And then we have this quantity. So this s over square root of n. So this sigma, it's estimated to be s, and then we divide by square root of n. And we have seen that this is, by the central limit theorem, this is approximately the standard norm distribution, right? Now, let me remind you, and since we have done this so many times in the previous classes, in the like in Stat 311, I'll not discuss this in details. There's a standard normal distribution. So this is a z. Okay. Suppose this is alpha over 2. Then we call this point, well, this is also alpha over 2 due to the symmetry. We call this point z of alpha over 2, the critical point. Okay. And due to the symmetry, this is called minus z of alpha over 2. This is just notation. Okay, so for Z, which is standard normal. Okay, and you have this entire machinery of those Z tables, and you can compute whatever you want using those Z tables, right? What we have therefore is, I can say that what is the probability, just like before, what is 1 minus alpha? Remember that 1 minus alpha is same as 1 minus alpha over 2 and alpha over 2. So that means I'm subtracting from 1 this area plus this area. So what I'm left with is this unshaded region, right? So this is really the probability of minus Z of alpha over 2 less than X bar. Okay, I'm using this Zn as a random variable. So it's approximately. So let me just write it later. Okay, so forget about that part for now. So I'm just writing, I'm trying to compute this. So X bar minus mu over S over square root of N Z of alpha over 2. What is that? So what is the probability that this random variable is between these two? Now, if this random variable is standard normal, we know this is 1 minus alpha, right? If it is Z, so suppose this is Z, then we know this probability is 1 minus alpha. But it's not Z, but it's approximately Z. So we can write an approximately equal to this. As I mean, when n is increasing and n is going to infinity, eventually it's equal to 1 minus alpha. But for a given n, this is approximately. Okay, so it's approximately equal comes from the fact that it's approximately normal. Okay, I hope that that makes sense. Using the previous calculation, so now I'm trying to get an estimate of mu. So what I'm doing is so 1 minus alpha is approximately equal to. So let's solve for this mu. So first of all, I'll multiply this S over square root of N minus mu. So it's Z of alpha over 2 S over square root of N. And therefore, 1 minus alpha, if I solve for mu, it becomes X bar minus Z alpha over 2 S over square root of N less than mu. X bar plus Z over alpha over 2. Okay. Once again, first you have to move this X bar and then you have to multiply with -1. So inequalities will flip and you'll get this. Good. So approximately this is the confidence interval. So again, letting little X bar and S denote the realized values of X bar and S respectively. After the samples are drawn, an approximate 1 minus alpha 100% confidence interval for mu is given by this interval. Okay, so it's X bar minus Z of alpha over 2 S over square root of N to X bar plus Z of alpha over 2 S over square root of N. That's the answer. Okay, that's an approximate 1 minus alpha confidence interval. It has another name. It's also called the. It has another name. It's called the large sample confidence interval. Okay, so the another name for this one is this interval is called a large sample confidence interval for mu. So the name of this one. So we have studied two different things. So for the first thing was just for like when we have a t statistic and we computed the exact like confidence interval for mu, and this is an approximate confidence interval for mu, okay, based on any distribution. Just like before, let's solve a couple of examples. So let's start with, say, so number 1. So example, it goes like this. Let the observed value of the mean x bar and of the sample variance of a random variable or random sample of size 20 from a distribution is following a normal distribution with mean mu sigma squared be 81.2 and 26.5 respectively. So what he's saying is that when we compute the observed mean, so it's 81.2, and the observed variance is 26.5. We have reasons to, and it's a sample of for size 20, and we have reasons to believe that it's coming from a distribution with n, which is a normal distribution with mean mu and variance sigma squared. Okay. All right. Find respectively 90%, 95%, 99% confidence intervals for mu. Okay, so we'll find a bunch of confidence intervals for mu. Okay, let's solve this. Now, first of all, this is coming from a normal distribution. So we know that the original distribution is normal. So the first method should work fine. By first method, I mean that we have the better estimation or the exact estimation, which is known for the case, this one I'm talking about. So 1 minus alpha is this one. So here the underlying assumption is the distribution from where the samples are drawn is normal, right? So we're going to use this result because remember the second result, by second result, I mean the one that I just derived is right here. So note the difference. So this was what I meant by the first result. This is what I meant by the second result. This is an exact expression. This is an approximate expression. The exact expression is based on the t statistic, and the approximate estimation or approximation is based on the when we consider a standard normal, right? So here we know that the underlying sample, so it is normal. So we can very well use the first one. If we can use the first one, we don't need to use the second one. So let's do that. So let's use the first one. Let's see. Okay. So what we'll be using is the first result. So we know that, so we have this 90%, 95%, and 99%, right? So this is going to be, well, I want to, but anyway, it's fine. Let me just mention it here. When we wrote this result, you see that mu is between these two. The only difference between the left and the right side is this is minus and this is plus. So sometimes the confidence interval are written as x bar plus or minus this quantity, right? So that's easier way of writing. Just wanted to mention, okay? So the confidence interval is x bar minus t of alpha over 2. What is the degrees of freedom here? So the sample size here is 20, right? So it's 20 minus 1. So n here is 20. So n minus 1 is 19. So this is 19, right? Okay, so let me just put it here so that I can write it side by side. So it's x bar minus this one times s over square root of n. What is s? So s is square root of 26.5 over square root of 20 to x bar plus t of alpha over 2, 19, square root of 26.5 over square root of 20. And I should have also replaced x bar. X bar is actually 81.2. So I should have written that too. Okay. So all it boils down to is finding this alpha over 2. So now, so let me just write it again. 81.2 minus t of alpha over 2, 19, square root of 26.5 over 20 through 81.2 plus t of alpha over 2 comma 19 square root of 26.5 over 20. So that is the interval we are talking about. So as necessarily I have to find this. But before doing that, I have to fix this alpha. Remember what is alpha? So alpha, I mean, again, if you recall, this value, whatever we have here, we call it p-value, it's alpha over 2, right? So in the first case, case 1, so we want to compute this for 90%, 95%, and 99% confidence interval. So what does it 90% mean? So we want this number to be 90%. So this thing, we have, sorry, this is not alpha over 2, this is alpha. No, this is alpha over 2, but so when we compute this, okay, so this is alpha over 2. And what we are having here is we're trying to compute this number, which is t of alpha over 2, 19, right? Now, we want, again, let me just remind you. So this is the formula that we have. So we have 1 minus alpha equals probability of this 81.2 minus t of alpha over 2, 19, square root of 26.5 over 20 less than mu less than 81.2 plus t of alpha over 2, 19, square root of 26.5 over 20, right? For the first case, and this is my 0.0. Okay. For the first case, we want a 90% confidence interval, right? So we want this number to be 90%, 0.9. So in this case, so if this is then alpha is 0.1. So alpha over 2 is 0.05, first one. Okay. If we want alpha minus 1 to be the 95% case, then we want this to be 0.95. So my alpha would be 0.05, I guess. Yeah, 0.05. 0.05. And that means alpha over 2 is 0.025. Right? And for the third case, if 1 minus alpha is the 99% confidence interval, so it's 0.99. So that means my alpha is 0.001, and that means my alpha over 2 is 0.005. Three different cases depending on the three confidence intervals. So it can be 90%, so it's a 90% case, and this is a 95% confidence interval case, and this is the 99% confidence interval case. Right? All I have to do now, I have to replace the values of alpha over 2 here, and I find this number. So let's do that. So for the case of alpha over 2 equals to 0.1, it is going to be 81.2 minus t of 0.05 square root of 26.5 over 20 through 81.2 plus t of, sorry, it's 19 should also be there, t of 0.05 comma 19 square root of 26.5 over 20. Okay. Let's focus on one case at a time. So alpha equals to 0.1 case. How do I find this number? T of 0.5 comma 19. Well, once again, let's go back to the table. What we do is we go to one-tailed. Now we have p-value. So in this case, this value, what we need is so what is our alpha over 2? So we have to put the value of alpha over 2 there. So and the alpha over 2 value is 0.05, right? 0.05. Degrees of freedom in the first case is 19. So hit enter. So you get 1.73. Okay. What I'll list it and then what we have for the second case. Okay, now let me just stop share. So the first case, the number here is, so this is equal to 81.2 minus, so this is really what we just found is 1.73 square root of 26.5 over 20 to 81.2 plus 1.73 square root of 26.5 over 20. And if you compute this, this is the interval 79.2 through 83.19. Okay. So the confidence interval based on this sample is this one. So and so 79.2 through 83.19. So the chance is that so your 90% chance is there that the mu is between these two based on the sample. Okay. What will be for the second case? So this is what we have done for alpha equals to 0.1. So for alpha equals to for the next one, which we have alpha equals to 0.05. That is a 95% confidence interval case. I have to just change the calculation accordingly. So let's do that. So for alpha equals to 0.05, that is my second case, I have the interval, confidence interval, equals 81.2 minus t of 0.025. Remember that we write here alpha over 2. So if it's 0.05, it should be 0.025, comma 19, 26.5, 20. Through 81.2 plus t of 0.025, 19, 26.5 over 20. Let's compute this number, t of 0.025. So I have to put this value and this value in the table. So let's again share the screen. So all I need is the p-value to be 0.025, and this value is already 19. So hit enter, and you end up with 2.09, right? So that is my value. So this t value is what I need. So 2.09. So it's really 81.2 minus 2.09 times 26.5 over 20 to 81.2 plus 2.09, 26.5 over 20. And if you compute this interval, this is going to be 78.79 through 83.61. Okay. The last case, it was this one, 79.2 through 73.19, and this one. And for the final case, for alpha equals to 0.01, third case, so the confidence interval is equal to 81.2 minus, I have to write alpha over 2 here, so it's 0.005, 19, 26.5 over 20 through 81.2 plus t of 0.005, 19, 26.5 over 20. Okay, so let's compute this number. So once again, so all I have to do is t of, so p value is t of 0.005, and this one is 19. So let's hit enter, and the result is 2.86. Okay, so I get 2.86 here. So it's 81.2 minus 2.86, square root of 26.5 over 20. 81.2 plus 2.86, square root of 26.5 over 20. So if you compute this, this interval is actually 77.9 to 80. Let me quickly check it because I have to check this by calculator. I'm just trying to see what this result is. So this is going to be 84.49, 84.49. Okay. All right. So these are the three results. So three confidence intervals. So please observe one curious fact that so first result was with probability 90%, you're certain about your answer. So here the interval is this one. Okay. Probability of 95%, you're certain about your answer, this one. Probability of 99%, this one. So the intervals, if you look at the intervals, they're increasing. So the first time the interval was, let's see, so it was 79.2 through 83.19, and you're confident 90%. So 90%, so times this is here. Okay. Next time, you're trying to have your estimate confident up to 95%. So your estimate becomes 78.79 through 83.61. So this interval is 95%. And finally, when you have 99%, it's 77.9 through 84.49. So it's even bigger. So this is 99%. So intervals are increasing, and that's no surprise, because if you're making your estimate more confident, so and you have more uncertainty, so this can be anywhere, right? So it can go anywhere. Okay, so as soon as the confidence intervals are increasing, the numbers are also increasing. Okay, so this is it. And next example, so let's do another one. So now I want to say this is example say 4.2.6. It goes like this. Let x bar be the mean of a random variable of size n from a distribution n of mu 9. Okay, find n such that p of x bar minus 1 less than mu less than x bar plus 1 is 0.90 approximately. Okay. That means this equality is approximately. Okay, this is giving us a hint that we should compare that with the formula that we obtained before. Okay, though here you can, since the original sample is normal, you can very well use the exact equation to find this number. But here they are asking what should be the value of n so that this is approximately 90%. So we'll be using this approximate formula. So let's do that. So let's compare this with the previous results. So we know. So what do you want? So we want we already know that probability that we know. So here's a solution. We know probability that x bar minus z of alpha over 2 s over square root of n less than mu less than x bar plus z of alpha over 2 s over square root of n is 1 minus alpha, approximately equals to 1 minus alpha. I'm just writing this result for a given sample. So please excuse my notation. So this was, I mean, this is right. So this was for this is the original equation. But when I have a particular sample, this x bar is becoming little x bar for a particular realization, right? And this s is becoming this little s for a particular realization. Okay. Or if you don't, here the no realization is given anyway, so we don't we may not need to use it. But anyway, so let's yeah, so let's just use big X here because no sample is given. So all these are capital S and capital X. Compare these two. If you compare these two, so that means I compared this with this. First of all, if you compare the right hand side, what do you get? So if you compare the right hand side, so 1 minus alpha is 0.9. So that means alpha is 0.1. Okay. All right. So as soon as you have alpha equals to 0.1, and so what we're trying to find, we are trying to estimate the n, right? So we have this equation. So if you compare this, so this one will be matched with this one. Same is true here. Since it's symmetric, one side is sufficient. We must have z of alpha over 2 s over square root of n is 1, right? Right. Now, what is for the sample? Well, this s is the sample variance, and actually the population variance is given, which is 3. So this is 9 means so sigma squared is 9, so sigma is 3. So population variance is 3, which is an and this is the sample variance. So I can very well use this 3 right here. So I want z of an alpha is 0.1, so it's 0.1 over 2, 3 over square root of n equals to 1. So what I have is n equals, so n is basically equal z of 3 times z of 0.05 squared. And z of 0.05 squared is, so we can find from the z table. So Z tables are in, I mean, we have done it in the previous class. So this is basically, remember what we have is, let me just remind you. So this is the 0.05. How do you find this? So this is essentially what we called phi of 0.05. Okay. And that we can find, so this is really Z of 0.05. We found phi of, so Z of 0.05 is a quantity. So that is obtained from the fact that this area is 0.05. This is Z of 0. Sorry about that. Okay, so now what we really need is the estimate of this one, and that we can find from the table. And if you're not comfortable of how to find this number, please send me an email or something, because we have done similar examples before. So this is really from the table we found it's 1.645 squared. So that is really, n is approximately 24.33. N cannot be an fraction, so that means nearest integers 25. So if n happens to be 25, so if you have a sample of size 25, the probability that the actual value of mu is between x bar minus 1 and x bar plus 1 is 90%. For that, you need 25 samples. All right, one last example. And that is, let's do 4.2.8 maybe, which is very similar to this one. That's why I'm doing. Okay, it goes like this. So let x bar denote the mean of a random sample of size n from a distribution that has mean, mu, and variance sigma squared equals to 10. Find n so that the probability is approximately 0.954 that the random variable or random interval x bar minus 1/2, x bar plus 1/2 includes mu. Okay, a very similar problem like the last one. So here's the solution. So what we want is 0.954 equals p of x minus 1/2 and approximately. So this one less than mu less than x bar plus 1/2. Okay, so that's what we want. Now, please note that we had a similar formula before. I think we just wrote it. So we know that 1 minus alpha is approximately equal probability of x bar minus z of alpha over 2 s of square root of n minus less than mu less than x bar plus z of alpha over 2 s of square root of n. Okay. So that means we need to see some alpha, right? So we observe that this is nothing but 1 minus 0.046, that is 0.954. So alpha is this one. So comparing alpha is 0.046. What do you need? We are trying to find some n, find n, right? So once again, observe that this and this are matching. Okay. So what we really need is we need 1/2 equals z of, we found alpha to be this one, so it's 0.046 over 2, alpha over 2. Now we have s over square root of n. So this is the sample variance. And the population variance is given to be 10. So I can very well use this one. So it's square root of 10 over square root of n, right? So this is, therefore, my square root of, so square root of n is 2 times, this 1/2 times, this is z of 0. Or maybe, so when I'm computing square root of n, so this 2 goes here. So it's 2 times 0.023 times square root of 10. And this number is equal to 1.995 from the table. Once again, if you are not comfortable how to find this number, please send me an email. We can discuss that. So that means if I compute n from here, I square it, and it can be shown that it's approximately 160. So we really need a big sample for having a random interval to include the value of mu. Okay. So we need about 160 samples. So if the sample size is 160, then so this is this number. If the sample size is 160, then we can safely conclude that a random interval x bar minus 1/2 through x bar plus 1/2. It's random because every time you draw a sample, this x bar changes, right? So this includes mu with probability 0.954. Yep. All right, so that is all about the hypothesis, the interval, the confidence interval that I wanted to talk about. So in the next class, we'll sort of build on this one and we'll do something else, okay? So thank you.